Great turnout already. I think with that in mind, we will get underway. Thanks for everybody who's joined us for another one of TEG Risk safety webinars that we wanted to, I guess, share with the safety community and in particular, I guess, the machine safety community here. Just to let you know, we will be recording this meeting, and there'll be some material that comes out afterwards as well. What I do certainly encourage you to do as we go along and present this material. If you have any questions, maybe chuck them into the chat. That'd be great, and we'll see if we can get to them at the end. We've allowed for a little bit of time there, so please do that. We'd love to get some feedback there. We have actually done a webinar previously on, I guess, the machine safety standards framework and how you can use that to your advantage and leverage it to just get the information that you need. And sort of this one here, this webinar, we've called it Uncovering the Hidden Nuggets and Machinery Risk Assessments and Standards. And we're sort of going a little bit deeper here. We're actually going to pull out various bits of information that are sort of hidden within the different standards that may be useful for you in terms of what you want to apply in your machine safety work. We're going to look at, we're going to have Charles Webb. He's been with TEG since 2017. He's got a really fantastic sort of skill set and qualifications that cover both mechanical and control systems. He's going to take us through that. He's worked regularly in various safety engineering life cycles, from risk assessment to design, validation. Recently worked on a project where he validated, I think, 10,000 safety functions actually through sort of combination of analysis and testing. So he's sort of been very, very deep into a lot of these different standards. And yeah, so I'm going to hand over to Charles to take us through. Thanks, Charles.
Thank you, Hamish. Can everyone see my screen all right?
Sure can.
Sweet as. Well, welcome to today's webinar. And as Hamish has already alluded to, my name's Charles. What we're going to be talking about today is the uncovering the hidden nuggets in machine safety standards, from inherently safe forces to functional safety. So my name's Charles, as he said, and I'll be presenting this webinar today. And I've got, really this is about demonstrating a few extractions and examples of control measures from our local and international standards. I've been with TEG Risk for about 8 years now, and prior to that, for about 9 years, I was a machine designer and a builder in various roles. And prior to that, I served my time as a fitter and turner. So yeah, fair bit of history there. Thoroughly enjoy what I do. And for those of you that have got your phones nearby, you can just scan that little QR code, and that's got my contact details and stuff on there. You can just chuck that straight into your contact list. It's just a standard V card. But with that, we'll carry on with the rest of the webinar. So a bit of introduction just to open things up. Really, there's a few key points that we need to make here at the outset, and I'll make it official. You'll hear more as we go on about this, but there's a few really important statements. First thing is that if you're going to apply a standard, the best thing to do is to stick with the scope wherever you can. Sometimes you can't do that and you get stuck. So that goes on to our second point. So these nuggets of information should be applied where, say, your standards-based controls are simply not defined. There's no information in there. You can't enact on them. So you need some kind of alternative solution, some kind of risk-based argument to support what you want to do. But the key measure here is robust risk assessment. That is the foundation before you start using other solutions and measures from other standards. So really important to try and use standards where you can. And I've also added in there to take all practicable steps, because ultimately people are interested in this, and it's partly legal as well. So definitely in New Zealand, we have the Health and Safety at Work Act, and what you do or do not do, or what control measures you put in place or do not, are a judgment call based on what you believe is all practicable steps, and so far as reasonably practicable. So just have that in the back of your mind as a bit of a litmus test as well. Am I doing everything I can, practicably anyway? So we'll cover a few things. I'll give you a little brief on our standards framework. Won't spend too long on that. And then we'll look at some key information. We're looking at hold to run controls, possibility of avoidance, and that dovetails nicely into our next topic, which is reduced speeds. And then we'll get into some more of the mechanical stuff, so reaching under machinery, reaching through apertures, and preventing whole body entry, and inherently safe forces. We'll look at all those things in turn. So as far as our standards framework is concerned, in Australia and New Zealand, we have our 4024 series of standards. That's for the safety of machinery. You'll see NZS is in brackets there because not all 4024 standards are observed by New Zealand, but they're all observed in Australia, definitely. And they all have a source, which are European and ISO standards in origin. So you can see an example of that. Now that's straight out of our standards. That's just a little structure that shows you how it works. But we've got our principles-based standards at the very top, and then we have our technical standards, which are in the middle, section B, and then our type C standards, which are specific to certain kinds of machines. Now, we have the same framework over here, which we've adopted, and we've simply numbered them differently. So you'll see in 4024, we've got our 4024.1000s and .2000s and .3000s. So that's our principles, technical, and type C standards specifically. And that's what the 1000, 2000, 3000 series refers to. I will state that the type C standards, or the 3000 series standards, are very specific. So you should never obviously violate the higher levels in that pyramid. But if you need something specific, perhaps where the higher levels are silent, type C standards are a great place to get specific solutions. If you're stuck and you need something that you can demonstrate as being proven or analogous to your requirements. So really good stuff in the type Cs and the 3000s. And we are constantly getting new and more 3000 series standards, adopting them from EN standards all the time. So if you didn't find something last month, you might find something this month. Okay, so we'll start into our first element, which is hold to run controls. We actually find that there's a lot of risk assessments and solutions put in place where people say, oh, you need to put in, wrap this thing in guards and put light curtains across it and all that kind of thing. And that can be suitable for automatic operation. But for very simple machinery where you've just got buttons or like a hydraulic lever where you're, for a bin tipper or something like that, you start asking yourself, is this truly necessary? And of course, if you've got a food processing plant or things like that, where hygiene becomes important, pharmaceuticals, things like that, you really don't want to have lots of welded bits of guards or bolts or seams or things like that, because now we're starting to put in bug traps. So it can be more appropriate to have a hold to run control. This is, I think, quite understated. there's a lot of presence and talk about performance levels and control systems and things like that. But hold to run controls are brilliant in the sense that they're an inherently safe design measure, and so they come under the category of manual control. And you can see that I've put a reference there. I've given you the specific clause to have a look at, but it does fall under a specific clause in the principle section. So that's really good. And it's simple to implement. You just have to observe a few things. You've got to have good ergonomics, because if someone's going to be standing there all day pushing buttons or pulling levers, you want to make sure that it's going to be ergonomic for the body. You've got to have a separate stop device, and that's a requirement for if a button sticks, then you have a backup plan, basically. Ideally, it's out of danger zones, but if any of you guys are functional safety, or you understand enabling devices, they can be in danger zones if they need to be. But ideally, everything's out of danger zones. Having a clear view is very important. So we want to be seeing the thing that we're controlling, and only one control point enabled at a time. So you can't have person A starting up a machine with person B is around the other side. And the other thing is we don't want to have the ability for someone to bump it or knock it and start the machine up. So it has to be guarded in some way, so that you must do a physical action to press the button. Once you put all those principles together, you can put a manual control point with hold to run control outside the hazard zone, and with a clear view of what you're controlling, and the problem's now been solved. Has its limitations. If you've got multiple people crawling all over it or hiding around corners, and you've got no visibility, then you can have issues. But if you follow the principles, you can go a long way. And there's a technical standard as well, which I didn't actually cite here, but for two-handed controls, they'll be required for higher performance levels, or if you need to keep your hands in one place. So if you're very close to a machine and you can get yourself into mischief. So then two-handed controls come to the fore there. So now we'll look at possibility of avoidance. This is straight out of 13849-1 2023. So that's an ISO standard. Now, just a bit of clarification on this. You'll see that I've cited the 4024 number as well, which is 1503. But you need to bear in mind that refers to ISO 13849-1 2006. So that's getting on for 20 years old. It's almost there. So it's well out of date and needs to be updated. But what we do is, in our line of work, if we know that the standard, for example, our local standard that we work with, which is 1503, if that's got a newer successor source standard, then we will defer to that standard. So that's how we will always do it, because eventually that standard will flow down into our framework anyway.
And it also represents sort of latest available knowledge as well. So it's the sort of thing that you can use to inform your decision making. And when you look at things like, so far as reasonably practicable, one of the requirements there is there a solution that was reasonably known? Well, if there's an international standard out there that's been published, you could argue that it's reasonable that the information in it could have been known.
Yep, exactly right. And that's part of our due diligence as well, so that we know what we're essentially talking about. And so anyway, this latest version of 13849-1 has a nice layout in there. It's in table A1. It talks about possibility of avoidance, and that comes under Annex A. And Annex A is guidance for determining your performance level required. So it comes in, there's three factors that you need to determine performance level. It's severity, possibility of avoidance, well, that comes at the end, sorry. Severity, frequency of occurrence, and possibility of avoiding or limiting harm. I'm going to focus on possibility of avoidance here. So that's the P value. That's P1 and P2. And what they've got here is a table with 5 considerations, 5 factors. And you would grade each factor, and then based on your score, you would score whether, in table A2, you can score your parameter P, whether it's P1 or P2. And the 5 key questions are: who uses the machine? How fast are the hazardous parts moving? Do you have space to escape? Are you aware of the hazard? And what is the complexity of the interaction? What's the task that needs to be done? Is it straightforward and simple, in and out, or is it complex? And certainly in our line of work, we've seen a need for this for a long time. So it's certainly good to see it coming out now.
And so that would, yeah, I was going to say this is a really useful tool for those that are doing your machinery risk assessments, and you've got your SFP evaluation that you want to apply to determine any required performance levels. Yeah, at the moment, the 402.4.15.03 version of ASNZS, it is pretty dated and it's pretty grey. It's not particularly informative. So this is a really useful tool to help you, perhaps refine your selection of your possibility of avoidance. And it may mean that, instead of being conservative and over specifying, you can actually answer those questions yourself with a little more clarity and maybe end up determining a required performance level that's actually, more aligned with what it should be.
Yeah, absolutely. And certainly if the hazard is more avoidable, then that also plays into less likely to occur. So for those of you that are using risk matrices even to do your risk scoring, these are all good factors to consider for your likelihood of occurrence of a hazard. So all of these 5 factors are basically, 4 of the 5 need some kind of judgment call, but one of them gives you specific numbers, and that's speed of the hazardous part. So we'll have a look at that. So we've got threshold values. So in these columns is red, yellow, and green. Obviously, green is the best score and red is the least. And in each column, there's thresholds for speed. So in the green column, you've got speeds less than 250 millimeters a second. And that's ideal. And in the middle column, you've got the 250 to 1,000 mils a second, and then finally in the red column over 1,000. So you can now determine. Well, that's one factor in your determination as to how avoidable a hazard actually is. And you'll see I've bolded the 250 millimeters a second for speed because you'll see that reappear quite a bit. But 250 millimeters a second is really good as a starting point to say a hazard is avoidable, but not always. You'll see that as you carry on with the webinar. A few examples. So for robotics, there's some safety requirements. Here's just one example. So this is the new ISO 10218-1 from 2025. So this year. Again, we have our local observation. So you'll see our Type C standard there. Now that's just AS, not NZS, just AS 4024.3301. So that's from 2017, and that refers to the 2011 version of the standard. So that's 14 years old now. So that's out of date, but this is the latest. So in the definitions, we talk about a reduced speed of 250 millimeters a second. Incidentally, robots are required to have the provision of lowering having further lowering of that speed so that you can, so that would be, say, a maximum out of the box, but you can obviously reduce that to suit the application that you're going to be using it for. Another good example for plastics and winding machines, sorry, plastic winding machines. So for winding up film or sheet onto a roll, we've got some safety requirements for those. And one example, there's different modes of operation, but one of them is if you need access into the machine, so you need to bypass the safeguards, the light curtains or whatever that are on the machine, you can limit the peripheral speed of those rolls, or sorry, I should say you're required to limit the peripheral speed of those rolls to 15 meters a minute. And what do you know, 15 meters a minute is 250 mils a second. So if you couple that with a nip point sensor as well, also a requirement of the standard, then that's no problem as a safety solution. So what you might be starting to gather at this point is you can say that a hazard might be avoidable at 250 millimeters a second, but you might start noticing that there's extra measures required. And you'll see that what you're going to find is taking things out of context can be a bit dangerous. And that's why we said in the beginning, context is really important and the entire solution. You'll see more of that soon. So don't be tempted just to extract one little piece of information and ignore the other control measures that might be around it, because they can be really important. So here's another example. This is EN 17449. So these are finishing lines and metal strip. So essentially we have a big coil on the far left, and as you can see in the diagram, we go through all the processing and then we go out to stacking at the other end. So you'll see there's a decoiler, there's feeders, there's cropping and shearing, there's straightening, forming. So there's a whole bunch of drawing in, nip and crush, shearing, pressing hazards, and all of those are present on this line. And yet this one Type C standard covers them all. So here's some really good examples of limited speeds. So yep, that's Type C standard. We've got two definitions here, which I thought you might be interested in. First one is a safety limited speed. So 3.24 or SLS. That's a speed that's limited by a safety function. So if we go outside the boundary of what is safe, or what we've determined as being safe, then the safety control system reacts and slows the machine down, whether it be by de-energization or whatever. Maybe it trips a safety function. But then 3.25, we have a reduced speed. So that's speed reduced without a safety function. And there's a few different speeds here. So you'll see your 250 millimeters a second has popped up again for robots and all non-shearing movements. But then you've got some really specific stuff around shearing and around presses. So if you're talking about guillotines, it's 33 mils a second. If you're talking about presses, it's 10 mils a second. And part of that comes down to giving someone time and space to avoid. So if you have a guillotine coming down, you've only got a window of maybe 50 millimeters less. It only has to be high enough for the product to get through, and then it has to do its job and crop. So you don't have a lot of space to get out of the way. And also you've got these two parts coming together. So they're shearing across each other, or in the case of a press, you've got two parts being squashed together to give a product its final shape. So there's no way you're going to get out of that. You know, a robot might knock you or, you know, push your arm up against something, but a press or a shear is coming down and there's no way you're going to stop it. So having that speed down to improve avoidability is really important. And that's part of the reason that those speeds are there. So again, if you have an application for a press or a shear, 250 millimeters a second might be a bad choice. But if you want to, if you have, say, a hydraulic press or something like that, this is a really good bit of information that you can apply as a limited speed.
And that's all shearing movements too. It's not just, presses, for instance. So there might be, different hazards on your own machines that you come across where there's shearing type hazards, and you've now got this bit of information that you can apply to your risk assessments.
Yeah, absolutely. Anything crushing or shearing between two parts, especially when they're dedicated parts, absolutely, you can definitely take that information and use it. So here's another one that we come across a fair bit. So this is safety of packaging machines. So that's been locally observed as 3407, that's AS 4024.3407, and that comes from EN 415-7. So this is about group and secondary packaging machines. So these are machines that essentially take a whole bunch of products and then pack them into a carton and then pack cartons into a case. So you're essentially grouping, cartoning, and then putting those cartons into a bigger case. And that might be for, cartons for retail and then cases for shipping. But the ideas are very much universal. So here's one example. Taking a rotating shaft end. If you've got a projecting shaft end, and it's smooth, and if you've got no projections on it, so no grub screws or pins or things like that, and it protrudes no more than a quarter of the diameter or 20 millimeters, whichever is smaller, then it can be considered safe by design. Now, if there's a risk of entanglement and you're in an environment where no one cares, like it's a very dirty environment, perhaps it's quarrying or mining or something like that, or even just conveying in a warehouse, no one is too fussed about sort of cleanliness. So putting a bearing cap on is kind of beneficial because it keeps the dust and the dirt out, and it's all practicable steps that can be done.
And also the general safety standard for conveyors require that they be covered as well. Yep. There's actually an explicit requirement of that. And then the corollary to what Charles said, you may have environments where they're very high hygiene and bearing caps become a problem because there's extensive scrubbing and maybe there's those sorts of bits and pieces that become a bug trap. And there may be situations where it just becomes extremely difficult and you're looking for a risk-based argument as to why in certain circumstances you don't fit those covers and you need, to be able to say why it is or it isn't a high risk. Well, these things help support that argument if you deem that's appropriate. So again, robust risk assessment still required, but it's the sort of thing that you can throw into your argument to say why you may not put a cover or a bearing cap over a rotating shaft on a conveyor in certain really difficult circumstances.
Yeah, absolutely, and it's a great way as well to demonstrate, hey, look, we've done all practicable steps. We've taken the sample out of the standard. We can now clean our conveyor. Obviously, hygiene for the many is also very important as well, rather than safety for the one necessarily. But absolutely, you can say that you've done all practicable steps if you can say extract a piece of information out of a standard and apply it straight to your application. And I mean, to be honest, looking at that photo, that could be a bearing anywhere. It wouldn't have to be on any particular device. It could be a conveyor as part of a packaging machine, which would fall under the scope of that standard. So when you start thinking like that, you can take these analogous components that you can utilize elsewhere. They become very useful. And that's why I say as well, they may not be suitable for all situations, because certainly if you can put a bearing cap on and keep all the dirt out, do that. It's easy enough to do. Okay, so for reaching under machinery, I've got a bit of a scenario here for you. So if we have a machine, it's just a packing machine inside a meat plant. So we've got, blood, fats, proteins, all that sort of stuff everywhere. And there's a 150 mil gap between the base and the floor. we've got some kind of transmission hazard inside and some kind of amputation risk. Let's say it's located 550 millimeters above the lower edge of the machine, but less than 850 away. What does ASNZS 4024.1801 tell us what the reach size should be? So if we have a look at our table, if you have a gap that's greater than 120 millimeters, a gap greater than 20 millimeters, your reach is 850. So the limit for reaching is 120 millimeters. So you've got to have a gap of 20 mils to the floor maximum. And don't forget that our standards consider anyone over the age of 14. So 14-year-old girls are completely legitimate as far as 1801 is concerned. So what are the implications then? What do you have to do? You now have to start extending your guards down to the floor, putting skirts around things, bolting mesh underneath the machine. But you need to be able to clean, because you've got packaging, you've got anything that gets dripped or lost off the conveyor will now go straight down to the floor, and you need to be able to clean it out. 4024.1 in this case, or 1801 specifically, does not have all the answers. We're talking more about principles based, and if you can stick with 1801, definitely do it. Definitely do it. But if you can't do it, if there's a reason, if it causes other issues, then there are ways around that problem. There's a bit more information here than what I wanted, but I decided to keep it in here just to give you a demonstration. So we're back to packaging machines, AS 4024.3410, and that's the general requirements for all packaging machines. You've got, I'll try and weed this out a little bit, you've got a 20 mil gap or less, you're back to 1801 basically, and you've got a gap greater than 240, now you have to bolt fixed guards on underneath the machine. So those are the two boundaries, which I'm not too fussed about, but the point of interest here is gaps that are between 20 and 40, and gaps that are between 40 and 240. And sure enough, your safety distance is now 550 millimeters. So for that scenario that we had before, you can apply 3410 and there's no problem with that machine. Same again with the gaps of, there's 150 more gap. The gaps of 40 to 240, again, if your hazard is 300 mils above the lower edge of the guard, like in our scenario, and the safety distance is, then the safety distance has to be at least 550. As long as you do that, and the gap's in this range, there's no problem with that. And the reason for that is because people need to be able to do their tasks. And one of the best things that you can, if you want to be sure of having an accident, the best thing you can do is to try and keep people out of doing their tasks, because they'll find a way to do it. And we see it time and time again in our line of work. So giving them access that they need is really important.
And the other thing I'd add too, that 550 millimeter distance is actually what 1801 talks about as being an acceptable safe reach distance from your elbow to your fingertip. So those numbers that you see there in that packaging standard have actually come from anthropometric data. That's human body measurements, for over 14-year-olds. So there is an element of universality applied there. It's not a random pluck number. They've applied a basis of risk to it, and they've set that 550 millimeters based on that. Now, I don't have a 550 millimeter long forearm to fingertip. I'd probably be in the NBA if I did, but that's where that number comes from. And it's just another way that you can infer, okay, there's a risk-based approach, based on some anthropometric reach distances that maybe you could apply into your risk assessment if you don't have clear answers for your particular use case.
Yeah, I had some regrets about not putting that in there. I was tossing up whether I should or not. So I'll see if I can find it. But yes, it is an 1801. That 550 millimeters, it is anthropometric, and it's straight out of 1801. An interesting point here that they've said, if you can't foresee that people would need access, you can reduce that distance further down to 130 millimeters. So what would make access not foreseeable underneath? Something alternative. You give someone an interlock door that they can swing open and get in to do their job. Why would they need to reach underneath? So that's one of the really good things about applying these Type C standards, is that the risk assessment, the design, all of those aspects have already been considered by someone. So a lot of that groundwork is already done. And if you have
yeah, I was going to say, also highlights the importance of good risk assessment.
Yep.
Competent people drawing on all of the relevant information and factors.
Absolutely. Okay, so now we'll talk about reaching through apertures, and again I'll call on 3410 because they are very specific. So apertures, it sounds like a photography term, like for cameras and stuff, but it's actually it's a very standard term, and it's, when we say apertures, we're talking about the passage of product. So whether it's product itself or cartons or cases or whatever, to go into a process and then come out the other end. Whatever that looks like. So as far as 1801 is concerned, you have any round or square opening that's greater than 240 mils, that doesn't prevent whole body entry. So, anyone who's taken some time to look around in a supermarket and see those big cardboard cases will know that those things have to be passed through a machine, and they are definitely bigger than 240 mils. So what are we going to do now? Are we going to put light curtains on all of our openings? Well, the answer is no, you don't have to. You can have more generous opening sizes, which is outside the realm of 1801, but there are additional measures that go with that. So here's an example. I'll just give you some kind of idea of a layout. If you have a packaging machine, and again, this is straight out of the standard, you've got your box essentially, which is fixed guarding, and then you've got your door D, that's really important, interlocking movable guard. You've got your hazard zone Z inside, and then you've got a whole bunch of dimensions. So you've got S, which is reach from the end of the tunnel. You've got your little tunnel on there, height, width, and length. All of those will make up the solution that I'll talk about now. There's a whole raft of options here, but I'll just focus on the one. Let's look at medium range openings. The reason I'm looking at medium range is because if it's small, you go back to 1801. If it's large, then you're going back to light curtains, interlocked powered guards, all that sort of stuff. So those are very standardized solutions. But the medium range is what's interesting here. So what's medium? It's got three categories: M, A, B, and C. But the entire medium range falls into 120 by 120 up to 500 by 500, and then also your slots, which extend vertically and horizontally. You can see all those dimensions there. But that's the family of opening sizes that I'll look at now. And they give special provision for anything to pass through as long as you have some additional measures. So if you were to put a tunnel guard onto that machine, then you would have, depending on what size opening you've got, you're going to need to have a tunnel guard, say 500 to 1,000 long, depends on what category you fall into. And also a safety distance of, say, 850 to 1,100, depending on what size the opening is as well. And that's really about how far you can roll your shoulder around to reach into the machine. And there's other configurations too. I didn't want to blind you with tables and numbers and stuff, but it's all in EN 41510, 3410 for the locals. But if you don't have tunnel guards, with or without conveyors, or if you have bent tunnel guards, all of those have values that you can apply directly to your application. And if we're talking about product going through a hole, that's really what we're talking about. You can apply that to any machine. What's the key though? You got to have an interlock door. So that was one of the requirements. I'll go back.
As well as the tunnel guard.
Yeah. So if you don't give anyone a means of accessing that machine, they're going to find a way to get in there. But one of the requirements for having that tunnel guard for this application anyway is you must have an interlocking movable guard. So that's one of the prerequisites. So again, to underline that importance, don't take out the tunnel guard only and forget about the interlock door, because that's really important. Another example, this is about ASRSs, and that's EN 578, oh sorry, 528. So again, 1801 says if you have a gap greater than 180 or a slot or a 240 square around, you're going to get whole body entry, or should we say you haven't prevented whole body entry. EN 528 gives you some specific ways that you can get around that to prevent whole body access into an enclosure. Just to give you some clarification, ASRSs are automatic storage and retrieval systems, and they are crane based usually, and they can handle anything from tote bins all the way up to 1 or 2 ton pallets of whatever, butter, cheese, anything else. So they have huge capacity, and they tend to be in a large room by themselves, isolated. So what you're seeing here is a way of getting into that system where the product passes through.
I think one of the interesting things about this one too is there's also a lot of other machine-specific standards, pallet wrappers, palletizers, etc., that will have different requirements to this.
Yep.
And those requirements might be light curtains, for instance, and that's where it's really important when you look at your situation to also be thinking, hey, I'm not just going to go grab the EN 528 requirements because it's easier. You've still got to be looking at the total context and what is the situation. I'm looking at a stretch wrap, automatic stretch wrapper. There is an AS standard for automatic stretch wrappers. That should be your first go-to, and utilizing that. This is just to sort of, I guess, highlight the fact that, for certain situations and where that's not possible to apply, you might be able to utilize some of these points and that they exist.
Yeah, absolutely. I really disagree with people that don't want to spend the money on light curtains, because if the light curtain is the most appropriate solution for the task, then use it. That's the short answer. Don't try and shortcut things and then try and argue why it's okay. Always try and follow the standards wherever you can. Stick with the scope. But if you get stuck, there are ways around it. So this one uses a combination of a height limit and a length of a tunnel guard that's required, and that's about preventing whole body entry. Okay, so we're nearing the end now. So we've got inherently safe forces. So this is about, I actually love this little annex of AS 4024.3410. Annex B will give you a list of a table of the maximum forces and pressures that can be applied to the body. So that's about crushing force, impact force, and static pressure.
Probably just important to if you just tell people what an inherently safe measure is, what does that mean in practical terms?
Yeah, right. So inherently safe means it's not going to cause an injury. So
a significant injury may cause a black fingernail or something like that, but a significant injury in the context of machinery. Yeah.
So the worst case would be first aid, I would expect. So crushing force, impact force, and static pressure. So what those mean is, yes, you have the forces applied to the body, but then you've also got static pressure, which is the pressure applied to the skin. So what we're talking about here is if you apply 13 kilos at knife point, then that's going to really do some damage, right? So let's take your crushing force of 130 newtons over here. If you apply 130 newtons at knife point, that's going to cause some serious damage. But if you apply it, you know, on a foam pad, you're going to cause no injury at all. So the pressure on the skin surface is really instrumental as well. So you need to think about what the applied force actually is, and how the pressure is being applied to the skin, the shape of what you're actually driving onto the body. And the other good thing is that Annex A shows you how to calculate it. So for those that are dealing with mechanics, they've given you a method to deal with that. I'm not going to go into details there, but it tells you how to calculate energy and force. But one of the big ones for me as a designer, this was really valuable for me, because when I work with pneumatics, I need to know, well, I can now calculate what forces my cylinders are going to exert on a person. So I can go back to my force calculations, force and area, force as a result of pressure and area, I should say, for extending and retracting. Obviously, retracting, we're looking at the annular area of the piston, so with no piston rod. But what that means is now you can calculate exactly what force your cylinder will exert, but also you can now design your system with a cylinder that won't cause anyone any harm. Now, for example, if you had we see it a lot, product pushers. So, for example, you see them on check weighers. So, product comes along, check weigher weighs it out the other side, and a pusher will reject it. Or perhaps a corner transfer where a pusher will push a case onto the next conveyor. They can need higher forces for larger products, but often you don't need much at all. Obviously, the easiest thing to do is to get rid of a pusher altogether and just have compressed air, like blowing packets of chips or whatever. But if you have something heavier and you have to push it, then limiting your pressure or your physical cylinder size, that will help you comply to the standard. And that's a good demonstration. If you can stick with those forces, that's an excellent demonstration of, well, we've done all the practical steps and we've gone with this because, well, here's a good example. When I went to one place that had pushers on their conveyors, we took off the covers at the back of the pusher, and it was absolutely disgusting. I was starting to dry retch. There was just gunk and crap everywhere. It was in a food processing facility, and they tried to guard this thing to make it safe. But in doing that, they had made a bug trap, and it could never be cleaned. So you can get rid of all of that if you have a cylinder that operates, a pusher or a component that operates with an inherently safe force. So I would definitely recommend that table especially for the pneumatics guys. That could be really useful. But yeah, as an example, a 16mm cylinder at 6 bar, that'll push about 120 newtons. So that'll keep fingers in that safe typically. So I know that doesn't work for everything. And if you can wrap a guard around it and put it inside an enclosure, sure. But for some applications where you need to have it open, that can be quite useful.
Just a time check, Charles. Yep. We're at 10 to 1. It'd be good to get a couple of questions in at the end if you want to sort of move on and try and.
Well, that's good because I'm at the end now pretty much. So just drawing on some conclusions here. Really important to have access to standards. So getting access to those standards, what kind of machine am I working with here? Is there a standard for it? If there is a standard, use it. Make sure that you align with our standards framework. So try and use your principles first, and then work your way down the technical standards to your type Cs if you need them. don't use anything obscure or left-wing. Try and stick with our standards framework, and then step out more and more internationally as you need to. If you're going to get a consultant or an internal subject matter expert to do your work, make sure they're competent and they know what they're talking about. But the key statement here is a robust risk assessment is fundamental if you want to have the right solution. So often we see that they're not. So get a good solid risk assessment down, and you'll be on your way. That's pretty much it, guys. Yeah, questions?
Okay, so we have had a couple of questions raised in the chat. So we've got one question here from Bruce. The question there was, if there's an Australian standard and not a New Zealand standard, are we required or compelled to use the Australian standard? I guess what I'd say there is our primary requirement is the legal duty, and that legal duty to do so far as reasonably practicable. And when you dive down into so far as reasonably practicable, one of your considerations is what ought to be known about, available solutions. And so that's basically going to come down to which standards actually give you the most, I guess, reliable, useful, up-to-date knowledge. So I know there's a New Zealand standard, NZS 1657, that hasn't been updated in donkeys, and there's a purely AS 1657 version that has been updated far more recently, includes a couple of clauses embedded in it, which I do think add reasonable information to it. So I would say in that instance, it's not so much that you're compelled to use it. I think weighing up the value of that standard, it is a useful standard to use because it's what could be reasonably known. And that then may flow up to the European standards where, potentially there is useful information there that an Australian standard doesn't have. So I think it's about, asking that question around what's the useful information and the latest information in the context of what we're looking at. I don't know if that answered the question, Bruce. Let us know, maybe thumbs up in the chat or something like that. Smruthi, you've come in and said, Charles, you mentioned danger zones earlier when discussing hold to run controls. How do we determine what a danger zone is?
Okay, so that's pretty simple. So that's the stuff that's going to hurt you. So if you have a machine with moving parts, the danger zone is where you're going to get your fingers chopped off or your arm crushed, or it's not going to be standing next to the machine, right? So if I'm standing next to a machine, that's not actually the danger zone. The danger zone is the stuff that can crush or hurt you. Standing underneath a bin tipper where it can be tipped onto your head, that would be a pretty good example of a danger zone where you don't want to be, and often overlooked. Actually, people don't think about those kinds of things a lot sometimes. So yeah, danger zone is the stuff that's actually going to cause you the injury.
Okay, yeah, give us a thumbs up or something like that, Smruthi, if that answers your question. Oh, yeah, we've got a thanks, Smruthi. And Randall has said, how deep do the Type C standards go? How deep do the Type C standards go? Is there one for, say, a grinder or a linisher, for example? The answer to that question is yes, there are, and they do go quite deep, very, very specific. I think if you are looking at those bits of equipment, they're really, really valuable. And I think if you tried to build up a risk assessment from first principles, you would struggle to get as specific or as detailed as what those Type Cs do. So yeah, definitely doing a search. And we've covered off in various webinars, but I would go to Estonian standards, Randall. It's part of the European Union. They have to conform to those same standards that Germany does when they put a linisher or a grinder on the market. And they're much, much cheaper. So if you go to Estonian standards shop, you'll be able to purchase them for a really, really cost-effective price. Just an observation there from Gary. Many times you see approach being select a solution to an identified risk without having done a risk assessment. Risk assessment is key to defining the right solution. Absolutely agree 100%. I think this flows a little bit on to that point that Randall made around Type C standards for grinders or linishers. There can be a desire to just cut straight to the solution that the Type C standard, for instance, might propose. And there's a good chance it might be adequate. However, that risk assessment does need to be done to validate that there are no other scenarios or issues that need to be accommodated in your own personal, your own sort of, organization's existing, I guess, situation. Because it may be that even though you've got a particular machine and a Type C exists, the way you use the machine or attributes of the processing that you're doing within it might mean that additional controls may be required. Hopefully that addressed that, Gary. And then we've got a question here from Andrew Walton. So we've got, when calculating a hazard risk number, so that's HRN, we use degree of possible harm, DPH, frequency of exposure, FE, likelihood of occurrence, equals HRN. In our risk assessment, we don't single out possibility of avoidance as a separate value when calculating the HRN. It's considered and included the selection of the likelihood of occurrence value. Should we add possibility of avoidance to our risk assessment HRN calc for PLR determination? We need as a separate component anyway. So there are a couple of different HRN calculation methodologies, Andrews, and one of them actually, so I think the one you're referring to is, I don't know if you could see that, that's actually in this book, which is Safety, Reliability and Risk Management Integrated Approach by Cox and Tate. That actually, I think, is the first reference document that referred to that particular calculation methodology that you're using at the moment. And there are others, like I think SIC, for instance, at one point, I think brought out a risk assessment methodology, which probably came from another paper at some point, which included possibility of avoidance in there as well. So it's up to you. I think it comes from a reference document. I think your method is fine as long as you have possibility of avoidance in your PLR calc. So I don't know if that answers your question. You could include it. It would just mean you're aligning with a slightly different methodology, which is also valid as far as I'm concerned. But your current methodology, as long as you have a separate evaluation for PLR, would be adequate as well. And we've got a point there from Kathy. Can you send us the details of the book, please? Yep, absolutely. I'll send that through. It was pretty hard to find. It sort of, in the end, I had to go through Amazon in the US to get it, but you can get it. I'll give you the specific ISBN number as well, so you can chuck that into Amazon if you need to buy it. We're at 12:58, so we've got 2 more minutes. Any more questions, guys? I'm going to chuck them into the chat. Oh, we've got one from Rachel. When the current AS/NZS standard is not as current as the EU standard, are businesses expected to also purchase these EU standards? Expected to purchase? Good question. I think you want to be making sure that you are aware of what the latest available knowledge is and what you should be applying. And some machinery that's gone in a year ago and then a new EU standard comes out, which puts some additional controls in place, there's not a mandatory legal requirement to go and upgrade to the latest standard. That would be done on, that may not be reasonably practicable. We don't apply it in a lot of other domains. The main thing is just to be aware of what some of those changes would be. I guess the challenge is, how do you know what's in those standards without buying them? Good question. Yeah, that's where I think it can be useful, certainly for larger organisations. They've got access to standards. I think through the Estonian website, you can actually buy like a time-limited preview period for a really low amount of money. And what that means is that you can actually puts it onto a timer, you can access that standard and basically read it and say, look, do I need to purchase this? And then you can make an informed decision on that. So yeah, good question. I think it's probably not one for larger organizations that could have good standards access, but yeah, there's other things that may want to consider. Or look, there's, people like us, if you want to drop us a line, we can probably give you a quick steer on things as well. We're in and out of those standards all the time. We can tell you if they're valuable or not. Look, Randall's just come back, says you can browse a standard for $2.44. That might be euros. So thanks. Thanks for that bit of info, Randall. So yeah, you can. 244 euros. You can browse a standard. So hopefully that's maybe a useful, a useful reference, Rachel, that you could make use of. Okay. Well, we've had a few people jump off and give them their thanks. Thanks very much to all of those. It's now bang on 1 o'clock. Just want to say, hey, for everyone that joined on, thanks very much. There's another one coming in another couple of months. There will be some stuff that comes out as far as in terms of an email and a bit of a blog as well, just as a bit of a refresher. And other than that, great to see you all, and we look forward to seeing you on one of our future sessions. Thanks, team.
Thanks all.